Chapter 6, Part 3, SN1 Reactions. SN1 reactions are unimolecular substitution reactions. So in this case, the rate of the reaction depends on the concentration of only one species. In this case, that is the concentration of the species containing the leaving group. So in an SN1 reaction, the first step of the mechanism is that the leaving group leaves on its own, taking that electron pair with it. When it does that, you end up creating an sp2 hybridized carbocation. And then the nucleophile can come in and it can attack from the front or the back. It can attack from either side of the carbocation, which will give you a newly substituted compound where the nucleophile has overall taken the place of the leaving group. The rate of this reaction is equal to the reaction constant times the compound containing the leaving group, which is often an alkyl halide. In an SN1 reaction, the nucleophile cannot attack from the back side. Typically, substrates that are used in SN1 reactions are more highly substituted than those used in an SN2 reaction. So if you think back to the SN2 example, that was a methyl group that had a leaving group. In this case, we're looking at a T-butyl group that has some sort of leaving group attached to it. So there's huge electron clouds on each of these methyl groups. This is actually a very sterically hindered carbon, even though we're trying to represent an entire methyl group with a stick. The nucleophile is not involved in the rate limiting step because the slowest piece of this reaction is going to be waiting for the leaving group to leave to form this not very stable carbocation. Once that has happened, the nucleophile is going to attack the carbocation very quickly because carbocations are highly reactive. Nucleophiles tend to have a negative charge, at least a lone pair. They're going to find that carbocation very, very attractive. And so that step is going to happen very, very quickly. The product is a racemic mixture due to the sp2 carbocation intermediate. So in our SN2 reactions, we saw that stereochemistry was inverted. In an SN1 reaction, you're going to end up with a mix of two enantiomers or possibly diastereomers, depending on how many stereocenters your compound has. But at least at the reactive center, you're going to end up with the mixture of enantiomeric forms. And again, this is because the carbocation is flat, and so the nucleophile is not locked into only attacking from the back side. It can also attack from the front. And those two options would give us opposite stereochemistry. So in this example, we have T-butyl chloride and water. This is a perfect example of an SN1 reaction. We have a highly substituted carbon with a pretty decent leaving group, and we have a fairly weak nucleophile. So the reason this is a good example of an SN1 reaction is, first of all, when the chlorine group leaves, it's going to leave behind a pretty stable carbocation, which I know we haven't talked about relative stability of carbocations yet, but that's coming in the chapter. And then also, because we have to wait for the carbocation to form, we don't want to react with a really good nucleophile. A really good nucleophile is going to want to attack and kick out the leaving group really quickly. So we need a more patient nucleophile while we wait for the leaving group to leave on its own. So in the first step of this reaction, the leaving group leaves, which gives us a carbocation plus our chloride. And then the water is going to come along and attack the carbocation. Now you might be wondering, why is the chloride not just hopping right back on? Well, definitely that's something that's probably going to happen, but you're going to have a lot more water typically in this type of reaction setup. And so because there is such a massive excess of water compared to chlorine, the water is more likely to attack the carbocation just because there's more of it available to do so. So one of the lone pairs on the water is going to attack the carbocation. And this leaves us with a positive charge on the oxygen. And I should also point out that these reactions are going to be at equilibrium. So far I've been drawing them with forward arrows. But these reactions forming the carbocation intermediate and then also the attack of the water, that's definitely going to be in equilibrium. So at this point, we have a positive charge on the oxygen because water was neutral and it attacked something positive. So now our overall species has to be positive. Another water molecule can come along and deprotonate. And that's going to give us T-butyl alcohol plus H3O plus and chloride as one of our side products. Now you might be wondering, why didn't I use chloride to pick up that proton? Well, kind of the same reasons. Chloride, if it were to pick up a proton, would create a really strong acid. It would create hydrochloric acid. And hydrochloric acid does not exist in water. It's going to exist as hydronium and chloride. Plus, there is such a greater amount of water, it's more likely that water is going to pick up that proton than chloride. So let's talk about the relative stability of carbocations. Let's take a look at methane. Methane is sp3 hybridized, which means it's tetrahedral. And if you were to remove one of those protons and create a carbocation, you would be left with an sp2 hybridized carbocation, which is trigonal planar. Notice that the unhybridized p orbitals come back to make an appearance here. The relative stability of carbocations is that tertiary carbocations are more stable than secondary, which are much more stable than primary, which are much more stable than methyl carbocations. Why? The answer is hyperconjugation. Hyperconjugation is when electrons are delocalized through partial orbital overlap. The more alkyl groups that are bonded to the carbocation, the greater this stabilization is. So for example, in this situation, we have a carbocation formed from ethane, or maybe from ethene, but you have two carbons, they both have a ton of hydrogens on them, and you have the unhybridized p orbital for our carbocation. Now, remember that orbital overlap is how bonding is created, and pi bonds are created through the overlap of unhybridized p orbitals. Now, we're not going to be able to make a pi bond here because we only have one unhybridized p orbital, but what we do have is the possibility of overlap between this unhybridized p orbital and the neighboring hybridized sp3 orbitals. And even though that's not going to create a bond, it is going to help delocalize the electrons, and that is going to stabilize the carbocation. So let's take a look at the stereochemistry of SN1 reactions. So in an SN1 reaction, the leaving group is going to leave in the first step. So that's what's being demonstrated here, is we have T-butyl bromide, and the bromine is leaving, and this gives us our sp2 flat carbocation. In our next step, the nucleophile can attack from either side of this carbocation. And again, this is what gives us two different possibilities stereochemistry-wise. So on the left-hand example, the nucleophile attacked from the left. On the right-hand example, the nucleophile attacked from the right. And notice how that gives inverted stereochemistry. So since this molecule is flat, there is no preference for left or right, top or bottom, front or back, whatever you want to call it. And so you end up with a 50-50 mixture, which is a racemic mixture. A process, such as a reaction, that creates a racemic mixture is called racemization. So there is another type of reaction that falls right in the category of SN1 reactions. And in fact, the SN1 example that we looked at before with T-butyl chloride and water was an example of a solvolysis reaction. A solvolysis reaction is a substitution reaction in which the solvent acts as the nucleophile. So in these reactions, typically you have a very large excess of the solvent, and then you have your substrate. In this example below, it's a 50-50 mixture of water and methanol. And you might recall from when we first learned about alcohols that alcohols are very, very similar to water as far as their chemical reactivity goes. And so they are both able to act as the nucleophile. Now remember, the first step of this reaction is going to be that the bromine atom leaves and takes the electrons in the covalent bond with it, giving us a carbocation. From here, we have equal amounts of water and methanol, and they are fairly equally likely to attack the carbocation in the center, which gives us either this alcohol from water as a nucleophile, or this ether from the alcohol as the nucleophile. And then this last option here, the formation of an alkene, is what we're going to study in Chapter 7.